yeah, Harun can always cut a little bit at the beginning if
Okay, we're live on YouTube too.
Hello.
Hey Marcus, hey James.
Hallo,
Hallo.
Hallo.
herzliche Glückwünsche.
Danke. Noch geheim.
Tag zusammen.
Ach, hallo Markus.
Hallo, Markus.
Hallo.
Yeah, I think we wait a little bit so that everybody gather because they are still coming. Yeah.
Okay, Marietta, I think we can start.
Yeah, we can
Right.
start and then we can admit people who come later. Yes. So
Okay, so I'm
please
very pleased.
volunteer.
Good evening.
Okay, so I'm very pleased to welcome you here in today's Lumer Lecture and present you Professor Dr. Rainer Nagel from the Eberhard-Karls-Universität Tübingen. He did his PhD with Helmut Schäfer in Tübingen, and at the end of the 60s and the beginning of the 70s, he was an assistant professor at the University of Maryland. And since 1975, he has been a professor of mathematics at the University of Tübingen, where he is currently at. Well, when I'm looking at here the Zoom participants, I would guess that most of the people here know him personally. Many of them know from his books and operator semigroup, the so-called Enger-Nagel short and full version, or from his books Arendt et al. About positive operator semigroups, or even from his latest book on operator theoretic aspects of ergodic theory. He has made significant contributions to all these fields and influenced the development in these areas also substantially. For example, via his more than 70 PhD students, or for example, setting up the Tulka Internet Seminar on evolution equations 25 years ago. It was probably the first online e-learning platform that at that time, and it's maybe only one of them which survived this long period. But I can surely say that probably this WG1 group of this COAST project is also influenced by him. So today he will speak about ergodic theorems, some Banach lattices, and takes us back 50 years. So there is a small notice. He asked me to tell you that there will be no room for questions at the end of this talk, but you are free to ask questions during the talk. So via chat or via Zoom. You can also ask questions in YouTube. So we are all set here. So Rainer, we are honored to have you here. Please go ahead, you can share your screen.
Thank you for this invitation. It's a pleasure and an honor. And probably my first talk giving in this format online. So what do I have to do? Share the screen or?
Yes.
Yeah. Okay.
Yes, fine.
Yeah.
Yes, we see it. Yes, it's
Okay,
fine.
that's it. So 60 years ago, Helmut Schäfer was a leading analyst at my university in Tübingen. For him and his mathematics, beauty was the first test. So he wrote and established, together with his students, a complete and beautiful theory of Banach lattices and positive operators. No applications whatsoever were needed. I was so fortunate to become his student and was fascinated by this style and his mathematics. 50 years ago, I was allowed to teach my first course and choose as topic Ergodic theory in Banach-Verbänden, Ergodic theory in Banach lattices. And the goal was to try to apply the beautiful theory learned from Schäfer to ergodic theory and dynamical systems. Now, let me first explain what all these words mean. So first, let's explain, sorry. Okay, so what is a Banach lattice? A Banach lattice is a vector space E endowed with a norm, making it a Banach space, and an order, making it a vector lattice. So suprema and infima should exist, and some compatibility conditions between the norm and the order. I think it's more helpful to give you some examples of Banach lattice. So the standard spaces, all LP spaces are Banach lattice. Spaces of bounded continuous functions is a Banach lattice. Then the dual space of a Banach lattice is again a Banach lattice. And some or many spaces of operators between two Banach lattices, E and F, are again Banach lattices. Okay, what is a positive operator? So T on a Banach lattice E is called positive if you have a positive element in E, then its image, so T of F, should still be positive. And special positive operators have a stronger property that they commute with the suprema and infima. So T of the supremum of two elements in E should be the same as T of F and the supremum T of G for all F and G. And these are not just positive, but are lattice homomorphisms. Okay, that's for Banach lattices and positive operators. Now, what do I mean by ergodic theory? Well, at least the starting point is quite easy. We take a measure space, a probability measure space, and look at the map from x to x, phi, which should be measurable, and in particular should preserve the measure mu, so mu preserving. That is the starting point of ergodic theory, and ergodic theory has a twin called topological dynamics, quite similar, just a different structure. Now you start from a compact space. So K compact. And again, look at the map phi from K to K, which now should be continuous. Okay, and the setting to the left we call a measure, an MDS, measure preserving dynamical system, and on the right TDS for topological dynamical system. Okay, these are the objects, but how are they related? How appear Banach lattice and positive operators when we start from ergodic theory or topological dynamics? And that's quite easy. We have this probability space x mu, so we can associate to it the space of all integrable functions L1, which is, as I explained above, a Banach lattice with its natural order, natural norm. And to phi, we can now associate a positive linear operator from L1 into L1 by defining T of F is equal F composed with phi. Now, these operators are not just positive, they are even lattice homomorphism, and it became popular to call them today Koopman operators. A special class of positive operators on the left on the Banach lattice L1. Now, in the topological case, we do just the same. We only take a different Banach lattice. We take the space of all continuous functions on K and define the operator, the positive operator, in the same way as the Koopman operator, now acting on the space of continuous functions. Okay, so we see that in ergodic theory and in topological dynamics, Banach lattices and positive operators appear in a natural way. Having been a student of Schäfer and in the heritage of Bourbaki, I felt that the goal and the goal of mathematics is to generalize, or one goal, and unify. And it's quite natural what one can do now to unify the two sides of this picture, the measure theoretical and the topological case. Instead of the Banach lattice L1 and CK, we take an abstract arbitrary Banach lattice, E, and we look at a positive operator on E. And we call this tuple E, T, now a lattice dynamical system. And clearly, the MDS and the TDS are special cases. So the question now was, and that was the motivation for my first lecture, that there exist a theory of lattice dynamical systems, generalizing and unifying the existing theory in ergodic theory and in topological dynamics. From this first lecture, I soon found two motivated students who joined me in this enterprise. And I also found a nice quotation from one of the big stars in ergodic theory, Halmos, who said that for ergodic theory and the limit theorems in ergodic theory, the proper context appears only when they are discussed in a general topological algebraic structure. And I proposed this general topological algebraic structure by looking at Banach lattice and positive operators on these Banach lattice. Okay, let me give you a few examples where this can be achieved, this unifying and generalizing. The first quite simple example is just concerns terminology. In ergodic theory, an important notion is ergodic MDS. In topological dynamics, an analog but different notion is a minimal TDS. And it's immediate just knowing a little bit about Banach lattices and that there are ideals in the Banach lattice, and to define irreducibility of an operator in the natural way that the operator leaves no non-trivial ideal invariant. So one has the irreducible LDS, and it's clear that in the above picture, when you associate to the MDS and TDS the LDS with the corresponding operator on the corresponding Banach space, an ergodic MDS and a minimal TDS leads to an irreducible LDS. So this is just notation, but a different second example. If we now take such an lattice dynamical system for any positive operator and assume it to be irreducible with spectral radius equal to 1, then it's a famous result already established before and also by Schäfer. If you look at the set of eigenvalues of T lambda with modulus 1. This set forms a subgroup of the unit circle. So we find some nice symmetry property for the eigenvalues of such an irreducible lattice dynamical system. And this is just one fact coming from the much more general Perron-Frobenius theory, spectral theory for positive operators. But it plays an important role in the two special cases of the MDS and TDS. Third example. Now we take again a Banach lattice, but not just a single operator, but we take a group. So group of positive operators. Acting on E, and we assume that this group is compact in the strong operator topology. In addition, we assume it to be irreducible, and just for simplicity, it's not needed abelian. that's the situation, then first there exists a fixed element in E, which is positive and even strictly positive. Just think of the functions, which means it has no zero, or the set of zeros is just a null set. So there, it follows that there exists just one such fixed vector. And there exists also a fixed vector for the adjoint operator in E prime, which again should be a strictly positive linear form. From the assumption, in particular from the irreducibility, follows these two facts. And this has enormous consequences, which I can draw in a diagram. So here we have our operator group acting on E. If we take the principal ideal generated by U, then clearly this is contained in E. And since U is invariant under T, the group G restricted to EU leaves E sub U invariant. The same holds in the other direction. We take E, the linear form defines a new norm on E. We take the completion, and again, the group G can be extended continuously to this larger space. So we have a sandwich, we have E sandwiched between new spaces. And these new spaces have very particular properties, because E sub U, now comes the general theory of Banach lattice. This is the principal ideal generated by one element. This becomes a so-called AM space with unit, and in particular, it's isomorphic to a space of continuous functions on some compact space K. Analogous result holds for spaces of this type, which appear here above. And again, such a representation theorem tells us that this E tilde is isomorphic to an L1 space on the same K with respect to the linear form U, which now becomes a measure on K. So we have E, the general Banach lattice, sandwiched between two very canonical Banach lattices. And even more is true, because you remember G was a group of operators on E. And it turns out, now turns out that the compact space K can be identified with this compact space G, which in addition is a group. So we have multiplication on G, and it now follows that the operator T of F, or applied to a function F, now we have either on L1 or CK, at some point H in H in G is just F times a fixed element T times H. So the operators, which initially are just operators on an abstract Banach space, now become operators induced by rotation on a compact group on a space which can be sandwiched in between the continuous functions and the L1 functions. And this is just a special case concerning generalization. The classical result for a single operator is the so-called Halmos von Neumann theorem. And here is one more example of the unification. Entropy is an important tool in ergodic theory, and in fact there are two kinds of entropies, the measure-theoretical entropy and the topological entropy. And my student Günter Palm found a common generalization and a definition of entropy for lattice dynamical systems. And together with Palm and Derndinger, we tried to write all this up. And at some point, we were unable to perform the necessary final revision. And in particular, we noted that almost nobody was interested in what we were doing. In particular, this paper on the entropy up to now has 0 citations. And the book manuscript, unfinished, and almost nobody noticed whatever we were doing. So we had to reach a decision. Palm changed work, become a neuroinformatics. Derndinger became a teacher, but still doing mathematics up to today. But the project Positive Operators and Banach lattice for ergodic theory failed. We did not finish, nobody was interested. And so Palm and Derndinger looked for a new job. I already had tenure in mathematics, so I could not just drop out. And somehow I came up with a different project, Positive Operators for evolution equations. And proposed to establish again an abstract systematic theory for positive operators related to evolution equations. And this case was different because the applications to PDE were immediate. And immediately, quite a few people got interested. In particular, I got again a number of brilliant young students. We published this book, we finished this book, and even this was in 1906, and this was 2017. So up to now, this is an active field with publications, and even the working group in your project is devoted to these semigroups. Okay, so around 2000, I was satisfied and prepared, or was looking forward to retirement. Admiring the work on positive operators and semigroups done by my former students, and was preparing to get ready for retirement. That was the situation at the beginning of the new millennium. But in 2006, unexpected events took place. The first was that at the International Congress in Madrid, Terence Tao got the Fields Medal for his proof jointly with Ben Green on the theorem of arithmetic progressions into primes. Two of my students, Britta Dorn and Tanja Eisner, took place and went to Madrid and took place in this Congress and came back to Tübingen motivated in telling wonderful stories about Terence Tao and his mathematics and the Ben Green-Tao theorem. And soon after, I got to read this paper of Werner Grad, the Green-Tao theorem, an ergodic point of view. And I remembered that we had tried to write a book on ergodic theory in the functional analytic perspective. So transitivity says, so from functional analysis to ergodic theory, from ergodic theory to the Green-Tao theorem in number theory. And indeed, I was looking up this paper or trying to understand, and I discovered, at least at a rather elementary level, some of the arguments and techniques we had developed previously for our uncompleted and unpublished manuscript. So why not try again? Look at the old stuff, look at the new results, and try to complete what we had begun 30 years ago. Again, I was fortunate to find a team for this new adventure. Well, it's not that we wanted to climb the famous Alpe d'Huez climb for the Tour de France, but the goal was somehow, or at least get near to the Green-Tao theorem by using our techniques and our knowledge on positive operators and on Banach lattices. This time we were much more fortunate, much more success. Indeed, we finished the book and we got accepted by the stars in the field here in Oberwolfach. So let me now explain to try what we did and what was different compared to the first attempt. And the title I would now suggest, Positive Operators for Ergodic Theory and Dynamical Systems, Topological and TDS, Topological Dynamical Systems. To make it more precise, I propose now structured ergodic theory. And I hope I will be able to explain what I mean by structured. And to make things simpler, I will now focus on the topological situation. It's technically and notationally somewhat simpler. So instead of ergodic theory, instead of measured dynamical systems, I will speak on topological dynamical systems. So always speak on K and phi. K compact, phi continuous. But not on a single, but on the category of such topological dynamical systems. And we already have seen that to such a system corresponds the Banach lattice C of K and the Koopman operator corresponding to phi. And these tuples also form a category, the C-star dynamical system. Because now it will be important to note that C of k is not just a Banach lattice, it's also a Banach algebra, and both structures are more or less equivalent. So you can look at it as a Banach lattice or a Banach algebra. I assume that you are a little more familiar with Banach algebra, so I will mostly now speak on the Banach algebra C of k. And in fact, and now it's quite easy to show that these two categories are equivalent. That means, so equivalent. It means that each property you can prove or talk on in K phi, there is an equivalent property on the system CKT. So they are basically equivalent, it's just a different language. So two languages speaking about the same object. And what's the difference between the objects? Now, K usually is a small space, a compact space, quite often finite dimensional. C of k, the dimension of C of k is always, except for trivial cases, infinite. So you go to a much larger space. But on the left, phi is nonlinear, while T is a linear operator. So T is a global linearization of in a larger space of a nonlinear system on a small space. Okay, and I should add a third category, again, equivalent. So we have CK, which is commutative C-star algebra. But we can also talk about an abstract commutative algebra or an abstract IM Banach lattice. And an operator which is either an algebra homomorphism or a Banach lattice homomorphism. So this a C-star algebra or an AM Banach lattice or commutative C-star algebra. And the theorem of Gelfand in the Banach algebra case and Kakutani in the Banach lattice case show that each element to the left can be realized as a CK and a Koopman operator. So it's the same basically, but we have different languages. So we can express the same thing in each of these languages, but now it depends which language you like more. And I want to show you now my argument why I prefer a certain language. You see, here we have our topological dynamical system and the phi. Now, Fürstenberg, Ellis, and some other big names tried to understand the structure of K phi. And they did it by looking at a quotient space, L. So we take a surjection from K onto L. L is a factor or a quotient space of K, and it should induce a new map psi. And the idea was to find an equivalence relation. So find an equivalent such that this quotient space is nice. And nice is called structured. That is a fundamental idea in topological dynamics, also in ergodic theory, to look for quotients, nice quotients, and then to build K out of these structures structured quotient spaces. Let's translate the structure in our picture of positive operators on Banach lattices. So now we have the Koopman operator on this side. Now this equivalence between the two categories is anti-isomorphic. So the arrows change direction. So while this was a surjection, this becomes an injection. So the continuous functions on this quotient space are now so we get a new operator here. This now becomes a subalgebra. It's no longer a factor, it's a subalgebra of C of k. And we should look for structured, nice subalgebras in C of k instead of looking for an equivalence relation making a structured quotient space. Okay, and least to find an example, a nice structured example is easy. So we define a new algebra, a subalgebra, as we take all eigenfunctions. So we take all f in C of k such that Tf is equal to lambda f, lambda of modulus 1, and take all these eigenfunctions, take the linear hull, take the closure. By the properties of the Koopman operator, this gives an algebra, and clearly this is a subalgebra of C of k, and clearly determined by eigenfunctions. So the eigenvalues more or less tell everything. So this clearly is structured, and it has a famous name, Kronecker algebra. And clearly this A defines a structured factor L. And now one can proceed in the same way. Look at the larger algebra than the Kronecker, which is still a structured subalgebra of C of k. So we can take relative eigenvectors to build larger and larger subalgebras to understand the structure of the entire C of k. So you see, we changed into an infinite dimensional setting, but now we have more structure in the Banach space, or in the Banach algebra, C of k. We have much more structure. We can talk about eigenvalues, eigenvectors, and use this more information, this structure, to build subspaces instead of quotients. And you see, just a reference. This is quite an active field in structured ergodic theory to build, and some people try to construct quotients. And here, Nikolai Ediko, Henrik Kreidler, and also Oskar Jamnischan try to construct subalgebras or sublattices, structured sublattices. So this is quite fascinating and quite a lot of activity going on in this field. I want to show you the value of going to subalgebras instead of quotients in a different example. So one more example why I propose to look for nice subalgebras instead of nice equivalence relations. Okay, the example or the problem is in topological dynamics. Now let's be very vague and intuitive. K, one goal in a topological dynamical system is to distinguish two opposite and different kind of behavior. So one tries to split the K into a conservative and a dissipative part. Conservative means that more or less the states have a recurrent motion. They start somewhere, but then somehow return to where, or at least return closely to where they started from. And the dissipative part means that the states go from A to B and do not return. That's useful and important to distinguish these two properties, a dichotomy between conservative or recurrent versus dissipative and wandering. So this is classical, and the classical tool to show that the system behaves, that it starts somewhere and finishes up in an attractor or in a fixed point, is via Lyapunov functions. So Lyapunov, in particular for engineers, is a very important concept. And now we start with our topological algebraic approach. So now we, instead of K, here we have K and phi. Now we look at C of K, and we have the Koopman operators T. And now we define, sorry, I should first mention, what I'm now telling is due to a recent PhD thesis by Kari Küster. Probably she's my last PhD student, who knows. So I report on her results. And so let's start again with some definitions. We have C of K and the Koopman operator. And first concept, F in C of K is a Lyapunov function. If it is sub-invariant, T of F is dominated by F. That's what we call a Lyapunov function. And clearly, the classical Lyapunov functions decrease along orbit, so it just means being sub-invariant. And now we want on the algebraic topological approach, so we do not look for a single Lyapunov function, but we look at all Lyapunov functions. Lyapunov function. And we observe that the product and the suprema of two Lyapunov functions is again a Lyapunov function. So it's quite easy if we take the linear hull, close it up, we get a closed subalgebra which is invariant under T. And we call L the Lyapunov algebra. And again, we know for the previous considerations, each such commutative algebra is isomorphic to some C of L. And we get a new dynamical system on this space, new compact space L, which is a quotient space of K, but we don't need this at the moment. We just know that C of L is a subalgebra of C of K. Now,
excuse me, there's a question, I think.
Yeah, please.
Rainer, do you assume those Lyapunov functions to be positive?
You can, because you can always add as a constant function 1 to make it positive.
Okay. Okay,
Yeah.
thanks.
So it's not, you can do it if you wish, but it's not, at the moment, it's not important.
Okay, thank you.
Okay, so now we have this algebra, and in algebras, we look for ideals. And I define the following ideal, Lyapunov ideal, J, by looking at, you see, we have a Lyapunov function, so f minus t, f is always positive. And we now look at the function g given by these differences. You see, the function g becomes 0 whenever f is equal tf. So these functions represent the situation where a Lyapunov function is strict or not strict. And now we take all these g's, look at the principal ideal generated by such a function. So now I write algebraic ideals, but you can also define the order ideals in the Banach lattice. We take the order ideal, we take the linear closed hull and close the linear hull and close it up and get an ideal, lattice ideal, algebra ideal doesn't matter. And again, we get an ideal which is T invariant. Having an algebra, having a closed ideal, or having a Banach algebra, a closed ideal. So it's just, you have to do the quotient space, L quotient J, which again is a commutative Banach algebra, is again a space of continuous functions. And again, it's invariant under the quotient operator, T invariant. Now you see we have 4 spaces, all left invariant by T. C of K, the subalgebra, the Lyapunov algebra. In the Lyapunov algebra, we have a closed invariant ideal and we have the quotient space. And let's try to visualize the situation. So we have CK and T. Now we have the subalgebra, so inclusion, the subalgebra, which is a space of continuous functions on some compact space. And the operator is just the previous T restricted to the subalgebra. Now, the Lyapunov algebra, we can perform 2 operations with this subalgebra. First, we have the ideal contained in L. And ideal is again invariant, and it's again the restricted operator T acting on J. On the quotient space, now this is now a surjection, yeah? Here, this is an injection, that's a quotient operator surjection. L quotient J. Again, we have the operator T hat on this quotient space. Okay, this is just algebraic operations. And somehow we have its L decomposed into a subideal and a quotient space. And now comes the first result, that the operator T, the induced operator T, acts quite differently on this ideal and on this factor space. Because if you look at the restriction T and its powers on J, one can show that it converges to 0. Pointwise, weakly, at the moment, that's not so important. So we call J the dissipative part, this ideal. The quotient space to the left, L over J, is now that the induced operator becomes the identity. So the dynamics on this quotient space is just the identity. There is no dynamics. While on the right, there is a dynamics on the operator level tending to 0. Okay, that's just abstract function analysis. And now clearly the final question is, let's look back. We want information in K, and we want, you remember the picture part, the conservative and the dissipative part. So dissipative is here. Clearly the identity is conservative. So we have now translate the information on this ideal and the action on the ideal and on the quotient space back to our original K and L. Okay, now pace out if you are very familiar with Banach lattices and ideals and closed ideals. They correspond to subsets. So the ideal J is all functions which such that f of m is 0. So there is a subset m in L. So the ideal, which is dissipative, corresponds to m in L. The quotient space, this becomes C of m. And I decided to just to show you what can be done on this abstract level, general level, by discussing a very simple example where you can see all the Lyapunov functions, the ideal, the Lyapunov ideal, the quotient space, and ask you to believe me that indeed it's a result which can be performed in general and not just on this simple example. Okay, here is my example. So you have the motion. Here there is a spiral converging to the unit circle. On the unit circle, you have a given speed on this circle, and the spiral approaches this speed. And then you take smaller and smaller circles, and you fill up the disk with the circles, each rotating with slower and slower speed. Now it's clear that a Lyapunov function, a TF equal less than F, clearly can exist on the spiral. But on the circle, because on each circle you turn back to where you started from, the Lyapunov function must be constant. So the Lyapunov functions are non-trivial on the spiral, but trivial on the entire circle, but different values on the different circles. So the quotient space, these are the functions. Now you look at the, you have the Stone-Weierstrass theorem. So the algebra is generated where these Lyapunov functions separate points, and they do not separate points on these circles because they are all constant, but they separate points on this interval, which corresponds to the different radii of the circle. So now it's clear the green is the conservative part, while the spiral is a dissipative part. And indeed, when you go along this circle, and that's the general result, in this quotient, the orbits on the dissipative part converge to each orbit converges to a fixed point. And the fixed point in this case is only here. And then you have other fixed points, no motion. And now you go back from, this is L, the space L. This is K. And now, so you go this way, and now this way, and you go back to K, and you have splitted K with this by this ideal and the subalgebra into the spiral and the green part. So this is then conservative, and this is dissipative. Okay, time is up. And clearly, this is just the beginning. Now, what can you do? You have the green part is again, can be quite complicated again. There's no global Lyapunov function, but you might have a local Lyapunov function on the green part. So a relative Lyapunov function. So you might be able to split up the green part again into a locally dissipative and a locally conservative part, and then keep going and build towers of such algebras. And okay, but that's left for more competent and more energetic hands. And here ends my journey. 50 years after, well, after first trying to combine Banach lattice positive operators with ergodic theory and topological dynamics. My report was a very structured history. The reality was quite different. Ups and downs, failures, some accomplishments. But in any case, to me, people were always more important than theorems, papers, and books. I had great teachers, wonderful colleagues and friends, brilliant students, and my family. I'm grateful to all of them, and thank you for listening.
Thank you very much, Rainer, for these nice insights in the last 50 years. So thank you very much. And let me also take the opportunity to wish you all the best today on your birthday, and very best wishes, I think, from all the participants here and also in YouTube. So yeah, happy birthday, and I just let you to join your family party and eat your birthday cake, and maybe you watch football as well. I don't know. But thank you very much for joining us today and giving this very nice lecture, and happy birthday again. Thank you.
Thank you for inviting me, giving me the chance to speak to you, and feeling still a member of your project. And good luck for your project. So, bye-bye.
Thank you. Tschüss und danke.
Thank you, Rainer.
Bye-bye.
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 Bye.
Danke, Rainer.